All right, so let's get started. So today's topic is on vector search, is on AI, is on RAG, is on reverse image search, and all of those cool AI related applications, right? And Tencent has been a longtime StarRocks user and contributor. In this webinar, Petri, our senior engineer from Tencent Big Data team, will talk about how they made StarRocks a fully fledged vector database and how they use it to power their various business scenarios, including their RAG applications, their image search, and many more. Okay, so let's welcome Petri to this webinar. And Petri, the stage is yours.
Okay. Thanks for Siddharth's introduction. Hello, everyone, and welcome to today's talk about StarRocks' new feature, Vector Index. My name is Pinecone Zhang, but you can call me Petri. That's my English name. I'm a senior engineer at Tencent Big Data in China, and I'm working for OLAP and vector databases now. The URLs of my GitHub homepage and email are listed here. If you have any questions about OLAP and vector databases, feel free to contact me through GitHub or my email. Today's talk has 4 sections. In the first section, I will introduce the background. We are going to take a closer look at our scenarios and the challenges that we faced and the motivation that drove us to make StarRocks as a VectorDB. In the second section, I will show our implementations and how we address the previous challenges we faced. In section 3 and section 4, I will showcase the actual use cases of how we use StarRocks as a VectorDB and give a summary about this talk. The first section is background. First, let's take an overview on StarRocks and its usage in Tencent. Generally speaking, StarRocks is an open source, distributed, and high-performance analytical database for big data. It offers sub-second latency for PB scale analytics and supports rich data sources such as HDFS, relational databases, and message queues. Tencent uses StarRocks extensively in many well-known applications. For example, you may know that our Tencent Games and WeChat and Tencent Video and Tencent Hunyuan, they are all using StarRocks for a wide range of scenarios such as ad hoc analysis and BR dashboards. Tencent StarRocks clusters have a total of over 20,000 of cores. That is a lot of cores, given StarRocks runs so efficiently compared to other OLAP databases, especially for our PB scale analytical queries. We have many PB scale analytical queries, and StarRocks runs very stably and fast. Before we actually talk about the features and implementations, let's take a look at a business scenario at Tencent that uses vector similarity search. Many of you may have used the text-to-image models before. These models use some text as inputs and could generate desired images. Tencent also offers such services. Training a text-to-image model needs a large amount of images, and we have already built a content library that houses billions of images. Model trainers must retrieve images from this large library for training or fine-tuning purposes. The image data format is shown here. The raw images are stored in the cloud, and each image is associated with some metadata. For example, the text descriptions of the image and the image source, image URL, image size, image quality, and so on. Furthermore, each image contains two feature vectors. One is the image feature vector, in other words, the visual feature vector. And the other is the feature vector above the text descriptions. For example, this picture is a tiger, and it may associate with a feature vector above the text tiger. There are two primary requirements to query the metadata and feature vectors. The first one is BR dashboards. These dashboards are needed to display trends in the number of images and statistics on image sizes and image quality and other information to help us manage those large amount of images. And the second requirement is vector similarity search. Include both image-based search and text-based search. For example, users can upload an image or some text descriptions. Then their feature vectors will be used to find the most similar ones in the database. For example, you can upload a picture of a tiger. Using its visual feature vector, we will find some similar pictures in the content library. Okay, this is the context. For scenarios related to vectors, for example, our context, our first thought is to use a VectorDB to solve the problem and meet the user's requirements. However, we faced some challenges to use an existing VectorDB. Generally speaking, there are three main challenges that we faced. The first challenge is scale and compatibility. And the second one is the complex research requirements. And the last one is heterogeneous workloads. In the next few slides, we will dive into each one. The first challenge we faced was scale and compatibility. Regarding scale, note that we must process billions of rows of data rows, and each data row contains metadata and two feature vectors. This data exceeds 100 TB. Therefore, we have concerns about whether existing VectorDBs can maintain stability and availability at such a massive scale. Also, bringing in a completely new VectorDB introduces potential integration challenges with our existing platform. The challenges including interfaces, the potential need to bring in more technology stacks and programming languages, and the integrations with our monitoring tools is also a challenge. Challenge 2 is the needs for complex search. Note that our scenario requires complex search over both vector data and scalar data. For example, we use top K search to find the K images most similar to a specific query, and we use range search to find images within a predefined similarity range. This picture demonstrates an example. We given an image, we need to find images within a predefined similarity range. Furthermore, we use hybrid search to find similar objects that satisfy specific structural constraints. For example, we will search for the most similar images where image quality is high and image size is larger than 10,000. And at the time our users proposed these complex search requirements, no existing VectorDBs could cover them all. Challenge 3 is heterogeneous workloads. Obviously, in our context, there are two different workloads over a single dataset. One is OLAP workload, which means relational queries for BR dashboards, such as the aggregation queries or join queries are all OLAP workloads needed for BR dashboards. And the other one is vector search. VectorDBs are efficient for vector search, However, they fail at analytical queries, such as aggregation queries and join queries. Although deploying multiple systems, for example, we use VectorDB for vector search, and we use StarRocks for BI dashboards. Using multiple systems may solve this problem, but this solution leads to data consistency issues, and it leads to very high maintenance costs to synchronize data across different systems. To tackle these challenges, one of the paths forward is to implement VectorDB capabilities within a system that already runs in Tencent's production systems. At Tencent, StarRocks has been working well for years and has been tested a lot in many different scenarios. It has rich tools for system management and maintenance. Our staff and developers are familiar with StarRocks and these tools. On the other hand, new vector databases don't have a full set of tools, and introducing a whole system from scratch into our platform involves very significant costs. Therefore, after considerations, we decided to build a VectorDB inside StarRocks. That is our solution to tackle these challenges. For challenge 1, scale and compatibility, our solution is to add vector indexes support into StarRocks. StarRocks is specifically designed for big data applications, and it can easily handle the 100 TB scale of our data. Besides, it allows us to use existing tools seamlessly. For challenge 2, complex search, we developed dedicated library and algorithms. StarRocks has already had a high-performance query engine. Therefore, equipped with our dedicated library and the new algorithms, it can efficiently process complex searches over a massive scale of data. Furthermore, with vector index support, StarRocks is capable to processing both analytical and queries and vector searches. This is an overview of our solution. Next, I will introduce the implementation details. First, let's see the details about how we add vector index support into StarRocks. This slide demonstrates the circle interface to create a table with a vector index. As the slide shows, here we have some columns, such as the document ID and a primary key and score, question, answer, source. These are some structural attributes to build the table. And the most importantly, we have a feature vector here, which named question embedding. Here we build an index named myIndex, which type is AHNSW on the column question embedding with certain index parameters. Our implementation support two types of well-known vector indexes, and they are HNSW and RVFPQ. They are very well-known indexes. And the L2 distance and cosine similarity can be used as similarity measures. Here are some query examples. As the slide shows, we can perform top key, range, and hybrid search through our easy-to-use circle interfaces. For example, the first query means that we want to select the top 10 most similar objects from a vector table by the similarity measure L2 distance on the column question embedding. And then the query optimizer will generate efficient plan to scan the vector indexes and return the approximate results. This slide shows the distributed storage model of StarRocks. Within a single table, the data is logically divided into several partitions. Furthermore, each partition is further sharded into multiple tablets. Tablets serve as the basic units for distributed storage and processing. Each tablet has multiple replicas for high availability. As this figure shows, here each tablet has 4 replicas for high availability. And our key contribution is to enhance the storage layer with vector index support. And the tablet data is stored in segment files. In other words, these files. And our vector indexes are maintained in separate vector index files for efficient vector search. Benefiting from the MVCC feature of StarRocks, our implementation naturally supports data updates. Whenever data is updated, new versions of both data files and index files are generated. Furthermore, each flush of the data files and the index files will trigger the creation and flushing of the vector indexes. Then both data files and index files are keeping immutable, and the system will periodically compact these versions of files to optimize the storage and performance. Most importantly, our implementation is fully compatible with all existing data importing methods in StarRocks, including streamload, routine load, brook load, and others. This ensures seamless integration with our existing data ingestion tools. Next up is solution 2, dedicated library and algorithms. We've developed TNN, a high-level vector index library. All vector index operations in StarRocks are now proxied by our TNN library. TNN serves as a general index library. It is created to integrate and enhance existing index libraries. Currently, it functions like a supercharged version of the well-known vector index library face. You may have known the library face, but we have some cool extra features. For example, TNN supports index catch, range search, and advanced block catch. In particular, TNN has advanced range search algorithms for the well-known graph-based index HSW and the quantization-based index RVSPQ. Note that range search over those two indexes are not supported in FACE, and to the best of our knowledge, no other libraries support these two features. Another novel feature in TNN is the block catch. In FACE, it reads indexes file by file. For example, we have many index files. If you want to query these files, using FACE, you must read a file into the memory. Then you query the index in the memory and get the results. If you want to search the other index, you must load a new index into the memory. This costs too much memory. Instead, TNN reads and caches RVSPQ index block by block. Comparing with FACE, we can achieve equivalent performance and accuracy while using half the memory with block catch. Next is solution 3, serving processing and workload isolation. With vector index support, StarRocks is now capable of handling both analytical and vector search workloads. What's more, we are actively developing new features, such as a serving processing engine and workload isolation to further enhance support for heterogeneous workloads. These developments are currently in progress, so we won't delve into the details here. We have conducted some benchmarks on our system. The left figure shows the results of the standard benchmark for VectorDBs. The benchmark named VectorDB bench. You can search the name in GitHub, and you will get the results and the source code. As you can see, now compared to the dedicated VectorDBs such as Milvus, Zilliz Cloud, or Pinecone, StarRocks has a medium-level performance. This is mainly caused by the phase overhead of our system. For example, we have very complex query scheduler and very complex query optimizer. They all lead extra system overhead for the vector search queries. And now we are trying to reduce those overheads and further optimize the performance of vector search. We also have some results from the production environment at Tencent. Generally, for million scale data, the query can be done in tens of milliseconds. More particular, we perform top 10 search over 1 million of vectors and we build HNSW index, and we use one machine. Finally, we got recall larger than 95%, and we got average 10 milliseconds latency. Similar, we got average 10 seconds latency for our 1 billion scale vectors with RVFPQ indexes and 26 machines. Section 3 is use cases. Case 1 is a typical RAG scenario for large language models. RAG, or Retrieval-Augmented Generation, is a promising technology that combines the power of large language models with external knowledge sources to enhance the quality and reliability of generated contents. It's like having a smart assistant that can look up the latest information on the spot, making sure you get the most accurate and up-to-date answers. Imagine you're asking a question to a chatbot, and instead of just relying on what the model learned during training, RAG can go out and find relevant information from a vast database. It takes the question, then search the vector database to retrieve relevant documents, and then it uses the found contents to generate a more detailed and accurate responses. Some chatbots in Tencent are using our system, StarRocks, as a vector database for RAG. Case 2 is the initial example we discussed. Recall that we have a really big content library containing billions of images. Each image is associated with some metadata, for example, image size, image quality, image source, and it has two feature vectors that represent the textual feature and the visual feature, respectively. There are two different workloads on the same data. One is OLAP queries for BR dashboards, and the other is vector search requests from users to search similar images. Previously, two separate systems were used in that scenario for BR queries and vector search. Later, StarRocks has successfully unified these two systems into one. It not only doubles the speed of vector search and also reduces total cost by half. Lastly, we come to the summary page. In this talk, I outlined the challenges we faced in vector similarity search at Tencent, such as scale and compatibility, and our complex search requirements, and the heterogeneous workloads about analytical queries and vector search requests. I also provide an overview of our implementation to address those challenges. In summary, StarRocks can be used as a VectorDB if you need to process billion-scale data with rich tool support, or you want to perform complex search with Circle, or support analytic and vector search workloads within a single system. That's all. Thank you.
Thank you, thank you, Petri, for the presentation. Thank you. And now is the time for you guys to submit your questions and get them answered. We do already have some questions lined up, So I'll read them out. Petri, you mentioned that Tencent, Tencent's a big StarRocks user using 20,000 plus cores in production, right? The 20,000 plus cores, is it in how many clusters? That is
Okay,
in how
okay.
many clusters?
Okay, thanks for the question. Totally, we have about more than 100 clusters, and the biggest cluster has thousands of machines.
Thank you. And the next question, I think in slide 21, you mentioned the benchmark, right? You showed a benchmark. What is the name of that benchmark test?
Okay, it's named VectorDB bench. Note that our
VectorDB
results
bench.
are not published in the official websites. We only perform this benchmark in
Okay.
our scenario.
Okay. Thank you, Petri. And the next question. Data updates will cause creating the new index and files. Does that mean we discourage the frequent data updates? So we don't do frequent data updates. Is it what it's saying?
Oh, sure, sure. Thank you for this question. It's a very good question. Actually, generally speaking, that's right. We discourage the frequent data updates. This StarRocks is an OLAP database, and it's designed for big data, and it's suitable for periodically data ingestion. If you for data ingestion, so we don't encourage frequent data updates, but we support data update periodic batch data updates. So the best practice is to batch your data and periodically import the data into StarRocks.
Thank you. So if I'm understanding correctly, so if you're using this vector index functionality, you should stay more on the batch side instead of real-time observes. Um, and the next question is, you've mentioned what you're doing with StarRocks for now. Are there any other use cases you're considering for it at the moment?
Oh, okay, okay. Thanks for your question. Actually, RAG and image content management and the large language models are main applications that we care about. Actually, we recently we don't have new considerations for other applications.
Thank you. And the next question, is it going to be available in the community version of StarRocks? And if yes, when? Yeah, I think I can take this question. Yes, Tencent, Petri and his team is contributing this back to StarRocks, and this feature is scheduled to be released with the next two-digit release, so 3.4 release. So you guys are join the 3.4 webinar. We're gonna announce later, and we're gonna talk about this again. Okay. Is there any other question? Will you upload the recording of this live? Yes, we will. In the Setter Data YouTube channel, we always do. I think this is all of the questions. Is there any more questions? Let's wait for another, let's say, 20 seconds. Okay, thank you. thank you everybody for tuning in this webinar. Be sure to join the StarRocks Slack channel if you want to learn more about vector search, hybrid search, vector search with joins, with aggregations, RAG, and all of those cool applications. Please join the Slack channel. We're all there, ready to discuss with 3,000 plus active members. So thank you everyone, and see you guys again next time. Thank you, Petri. Thank you everyone.
Thank you, Sida. Thank you, everyone.
Thank you.